Hi friends, welcome to our new session on control engineering for BE 7th semester mechanical engineering students. In this session, we are going to start with module number 3. In many of the syllabuses, the module number 3 is mainly consisting of time response of a control systems. So what is this time response of a control system and what are its benefits, that we will be knowing here. Let's know the syllabus. In the initial part, we will be knowing about steady state operations. In that, we will be knowing in detail the steady state analysis for a general block diagram for a control system and steady state characteristics with equilibrium in a system. Then we will be going through the transient response. Under transient response, we will be studying about the steady state analysis of a unit, step input and a general operation representation for a differential equation of a control system, and the distinct roots, repeated roots and complex conjugate roots or zeros, which are going to be the general form of a transient response. Then in the later part of a transient response, we will be knowing the stability criterion, that is using Routh's stability criterion method for determining the stability of a given control system. The next part, we will be going in detail with the root locus plots. Under root locus plot, we are going to know about how to plot the root locus and identify the salient points in a root locus and know about the significance of root locus angle and magnitude condition. Additional to that, we will be knowing about the breakaway points, angle of departure and angle of arrivals, and we will be plotting the root locus using the general rules and steps involved in plotting the root locus. And we will be getting to know more about the lead and lag compensation. Next, before going to understand about this topic, let's know what is time response of a control system. Here we need to know about the background of a time response of a control system. Most of the control system use time as its independent variable. So it is important to analyze the response given by the system for the applied excitation, which is a function of time. Means in basically control system, if we are going to control the time horizon or a time period, most of our controlling parameters of the designed systems are going to be in a stable zone. So to know about that one, we have to understand or analyze the nature of the control system when it is subjected to different type of inputs. So analysis of response means to see the variation of output with respect to time. So what type of variations we are going to get for the given input is going to be of a key interest. Next, this module will explain the concepts of time response, steady state analysis, transient response, and derives various transient response specifications. So here we will be knowing about the various transient response specifications, like what is the rise time, what is the peak time, then the delay time, and some aspects of settling or setting time also. Next, let's know some of the definitions and classification of time response. As we know, time response of a control system is how output will behave with respect to time. So it is important to know the definition of a time response. Time response. The response given by the system, which is a function of time, to the applied excitation is called time response of a control system. The time response of a control system can be classified or consist of two parts. One is the transient response. The second one is the steady state response. So when we observe a curve here, we see the response given for the given input. So this is the response. So here we see the response is oscillatory in the beginning stage, and it is going to get damped and it is going to get settled after a duration of time, and there is no change in output with change in time. So hence this period is called as steady state period, and before the reaching to the steady state, from the initial stage, this period is called as a transient response. This is like a bouncing of a tennis ball on a ground or on a cricket pitch. There we see it is going to oscillate, and then after reaching towards the boundary, so what it will be, it is going to get steady. So this is what is going to be one of the key aspects of any control system response. Hence, the final state achieved by the output is called steady state. As I have mentioned here, the final state, that is after a period of time there is no change in output, that state we call it as steady state, while the output variation within the time it takes to achieve the steady state is called the transient response. Means the time taken from the initial stage to reach to this steady state, this period we call it as a transient response period. So in every control system or any output of a control system, there will be certain duration of transient response. So in the beginning, to achieve the output, we need to have a certain gain factor. When we apply the gain, so what will happen? The system will oscillate in the beginning, and then after a duration it is going to settle down. Let's know what is transient response and later steady state response. Transient response. The transient response is the part of a response which goes to zero as time increases. So mathematically, for stability of the system, we write it as limit c of ct function of t equal to 0 as t tends to infinity. Here we are using limit as a function because here the equations are time dependent. As t tends to infinity, so it is going to reach to value equal to 0. That is the meaning here. the transient response may be exponential or oscillatory in nature. We have seen in the previous diagram. So the transient response it may be oscillatory or exponentially, and symbolically it is denoted by a letter small ct, and it is a function of t, hence it is written as ct bracket t. So here we can see one example of a motor which is rotating with a angular speed omega m. So here when we are going to plot the output response of this motor with respect to time and speed, the input command for this one is a steady input, that is a step input, and from this motor the type of response we are getting here are like this. So if it is having a slow response, it will be like this. If it is having a adequate response, so in the beginning it is going to be linear, then it is going to peak out and settle, and if it is having a oscillatory type of a response, so it will be peaking more than the set input and it is going to oscillate here, and after a period of time it is going to settle down. So usually when we are going to measure these motors of a shaft, we use the tachometer. In the tachometer we get to see the fluctuation of the RPM reading, that itself only, and we tell the people that wait until it gets steady. So the period until it is going to get steady, that period only we call it as a transient response. Next, steady state response. Steady state response, it is that part of a response which remains after completing the transient response and vanishes from the system output. Means the complete transient response is going to get vanish from the system output. So that period of time, from that period of time we call it as a steady state response. So steady state response indicates the accuracy of the system. Means the steady state response will be very near to the set input. So we happen to see that in the previous diagram also. Here the steady state, here we are having steady state, it is near steady state where is going to occur near to the set input. This is the set input. Output what we required here is meeting to the set input, that is the command. So here it meets the accuracy point. And the symbol for steady state output is CSS, steady state SS, CSS. Hence the total response, that is CT, can be written as mathematically CT is equal to, small ct is equal to C suffix t plus C suffix ss, where C suffix t, function of t, is for the transient response, C suffix ss for a function of t is a steady state response. Let's understand little bit more about the steady state and the transient response. Here we can see the output response, a slow response. This is the input which has been given, that is a command, step type of input. We need to reach to this point, so this point may be a 100% output. So here what is happening with respect to function of time t, the output c of t, the output c of t is going to increase. So at t1 this is the output, similarly at t2 this is the output. Okay, like this it is keep on increasing and it reaches to the 100% output that is the accurate value. And here during this period till here, we call it as a transient state. To reach near to the 95% of the output, then we call it also as a transient period. After that, whatever the time duration is taken and remains for that output, that part we call it as a steady state. So if it is having a slow type of a response, if we are having a unit input, that is 1 as a step input, so this is means at t equal to 0 itself only we are having the input, that is equal to 1, and for all values of t greater than 0, as t tends to infinity, means it is going to move towards infinity or a greater than 0, t tends to 0, t tends to infinity. Here for all values of inputs, so we are having the same output here, that is constant input should be there. But what we get, the response here in the beginning, we are going to have a peak rise. It is going to overshoot the output point, and after a certain duration it is going to damp down, and here we will be getting oscillatory type of a response, and we can see it is going to get settled, but there is an error with respect to the output and input. This error is going to be called as a steady state error, which is dependent on the designer's parameter, and here there may be oscillation, but this oscillation is quite acceptable when it is oscillating near to the target value or near to the output value. And this band where we are going to accept this one from the initial, this period from where we are going to accept the band for a steady state error, this one we call it as a transient response. This is a step input and this is a output response. As we have already told, total response is mathematically given as Ct is equal to Ct plus CSS. Next, for example, to tell how this can be implemented, if you happen to see an elevator, the elevator is going to be moving from the ground floor to the 4th floor. So this is the 4th floor, but the elevator is having passengers. They will be having passengers entering into this one. In the beginning it will be having high load, and by the time it reaches to the top floor, some passengers may be getting down at intermediate floors also. So what will happen, in the beginning the response will be slow and it is trying to reach the output. Here the output is the input command that is reaching at the 4th floor. By the time it is near to the 4th floor, the speed is going to reduce and it is going to get settled, and we are going to get to reach to the point of our elevator response. This one we see it in the malls also, where the elevators are being used and we see their response with respect to time. So mainly in controlling the motors, the induction motors for these elevators, or the rope drives for cranes, and for the belt drives, this time response plays an important and key role. Let's understand the steady state and transient state, taking one example how mathematically it is having its presence. Example, let us find the transient and steady state terms of a time response of a control system, where the output of a control system is given in the form of Ct is equal to 10 plus 5 e to the power minus t, or exponential to the power minus t. Here we can see that we are having two parts. One is the steady state term and another is the transient state. Here the second term, that is this term, the second term 5 e to the power t will be 0, as t denotes or it tends to infinity. When we are going to substitute here value of t, very high value, that is near to infinity, so that value will be equal to 0. Hence, so this will be the transient phase. So this is a transient phase. Okay, and the first term which remains t as we are going to substitute the value of t, this is going to remain 10 itself only. The first term 10 remains even as t approaches to infinity, hence that is called as a steady state term. So in our output response we will be having two parts. One will be the steady state term and another will be the transient term. So from the equation itself only we can get to know which are the parameters or which are the terms which are going to have the influence on our control system, and what parameter or what time period will be affecting the total response. That can also be evaluated. To know more about this one, so what we do is we try to know what type of inputs will be having its influence on the standard system. For that we need to know the standard test signals, which we will study now. As I have told, standard test signal. So it is very interesting fact to know that most control systems don't know what their inputs are going to be. Means we don't have any information about what type of input is going to be for a control system of a thermostat, for example, or a controller for a motor. So thus the system design cannot be done from the input point of view, because the inputs are going to vary every time, as we are unable to know in advance what type of input is going to come, or in future what type of input is going to be acting on these controllers. For example, just now I have mentioned for a thermostat which is there in a refrigerator. So often opening and closing of the door of the refrigerator, the temperature is going to fluctuate. So this type of fluctuation is going to be one input. For example, a servo motor or a induction motor. So we had talked about the lift. So in the lift we can see one person is going to press the top floor, second person is going to press the bottom or intermediate floors. So the motor has to work for these type of inputs, and in between the load means persons are going to get down from the lift and some are going to add into the lifts also, and some lifts are high speed lifts, some are slow lifts. So the system design cannot be done from input point of view, but when we are unable to know the type of input. But what we can do is certain types of test signals or known signals can be given to the controllers, and based on that what type of response or time response or the total response of the controller is going to come, we can know. as I have mentioned, the need of standard test signal. For example, when a radar tracks an enemy plane, the nature of enemy plane variation is random. Means if there is one enemy plane here, okay, and we are going to have our the Bofors gun which is going to target the enemy plane, but this is not going to go be here itself only until we have targeted. Behind this enemy plane, our plane also may be there. If I trigger it, seeing that it is here, then by the time it comes, it is here, by the time the missile is going to be launched, our plane will be in the next horizon, or the enemy plane will be in the next horizon. Our plane will be in its position. We may crash with our plane. So what happens? The radar system which is going to be monitoring the planes, or which is going to track the plane, has to be stable, and it should know what type of signal it has to provide. Hence it is very important. Then coming to the terrains, curves on the roads, etc. These are random, and these are required to be known to automobile system. For example, in our ABS system or in a cruise control system. So we can't give all these terrain curves as an input to the driving system, but for simulation and for testing we can provide these type of inputs. Then coming to loading on a shearing machine, when we are going to shear it. So initially when there is a block, there is a big block, so what is happening, or there are thickness of the block is high, so we are going to shear with the help of a blade. So this blade is going to apply the load on this one, and as it is having high thickness in the beginning, it will be having high resistance. As it is going on cutting down here, the thickness is going to reduce. That time we don't require the same load, so we have to control the load. So hence, as time is going to pass, we have to control the load. That is also required. So which load to be applied or thrown off, that all need to be known for a given system. Hence, need of a standard test signal is important. Now let's understand about need of standard test signal. Thus, for such type of inputs, we can expect a system in general to get an input which may be a sudden change, a momentary shock, or a constant velocity, may be a constant acceleration. Hence, these signals form a standard test signals. Therefore, the response of the signal need to be analyzed, or we can analyze for these type of signals what is the response it is going to get. So the above inputs which we had mentioned here are called as a step input, which signifies a sudden change; B, a impulse input, which signifies a momentary shock; C, a ramp input, which signifies a constant velocity; and D, a parabolic input, which signifies a constant acceleration. Let's understand individually these type of input signals and its response. First, the step input. Here, step input means at t equal to 0, here graphically we can see t value is going to vary from 0 to infinity. At t equal to 0, we will be having a step type of a input, or we will be having this type of input. Here it will be remaining, or input will be remaining constant for all values of t greater than 0. Hence the magnitude of this one is here taken as r. In some books they take it as a also. Means the response, input response, is equal to r times of ut for all values of t greater than 0, and it will be equal to 0. Here the magnitude will be equal to 0 for t lesser than 0. This signal signifies a sudden change in reference input RT. So here RT at a time t equal to 0. So it is going to be here, and it will remain constant. Next, applying a Laplace transform on both sides, that is on left hand side and on right hand side of the above equation. So Laplace transform of RT here will be capital R of S, where R is the reference and S is the domain, and Laplace transform of R into U of t. R is a constant, so it will be R. Laplace transform of U of t is 1 divided by S, hence it is given as R divided by S. Next, if we are having a unit step input, as the name itself tells, unit means 1. So here we will be having just a unit input, so this will be magnitude equal to 1, and it will be remaining 1 itself only for all values of t greater than 0. Hence here we are going to have 1 into u of t, that is equal to 1, and it will be 0 for all values of t lesser than 0. This signal signifies a sudden change in reference input at r of t at t equal to 0. Applying Laplace transform on both sides, that is LPT on left hand side and LPT on the right hand side. So LPT on these two, we get here, this one will be capital R of S, and this one will be 1 is going to be the magnitude, so it will be 1 itself only. Laplace transform of u of t will be equal to 1 divided by S. Next, we are having the ramp input, means here it is going to have a constant velocity. So change with the change in time, there is change in magnitude, that is magnitude is also changing. Here at t equal to 2 we will be having another magnitude here, and at t equal to 3 something we will be having another response here. But when we measure the slope here, the slope of this one, this slope is going to be a constant and this change is constant. Hence mathematically it is given as, in a time domain, small rt is equal to capital R into t, where R is here the slope, ramp slope for all values of t greater than 0, and it will be equal to 0 when it is less than 0. So here signal has a constant velocity or a constant change with respect to time. Hence applying Laplace transform on left hand side as well as on the right hand side. So Laplace transform of small r of t is equal to capital R of S. Laplace transform of this r into t, that is r is a constant, Laplace transform of t will be equal to 1 divided by s square, hence it will be r divided by s square. Next, we are going to know about a parabolic type of input. Here we can see there is as the time is going to change, here the output or response is also going to change, and it is increasing exponentially. Okay, initially it is having a low amplitude or a low rate of change. As time changes, it is going to increase, and it is forming a parabolic curve. This is a parabolic curve. Hence, it is given mathematically. This nature of this curve is parabolic. So hence, the mathematically the representation is RT is equal to capital R t square divided by 2 for all values of t greater than 0. So here this nature is R into t square divided by 2. So this one, when we apply a Laplace transform on both sides, that is on left hand side and on the right hand side, so we get here R of s, and Laplace transform of left hand side, that is here R into t square divided by 2. So we know Laplace transform of t square is 2 factorial divided by s to the power n plus 1. So 2 get cancels, so it will be 1 divided by s to the power n plus 1. N is here 2, so 2 plus 1 it will be 3, hence it is r divided by s cube. So this is the Laplace transform representation for a parabolic type of a input. Next one, we are having a sudden impact type of or a sudden load type of a test signal also to be given to a system. Here the magnitude of this value will be at t equal to 0 will be infinity, so it will be tending towards infinity. Hence we write this one as r of t is equal to delta t equal to 1 for value at t greater than 0 or equal to 0. Means at t equal to 0 we are having a magnitude that is tending towards infinity. Here the function has a unit value only for t equal to 0. In practical case, a pulse whose time approaches 0 is taken as impulse function. Hence it is given by Laplace transform of delta t is equal to 1. So impulse input response is going to be equal to 1. Let's summarize. Here we have put all the standard test signals in a table here, and its response in a S domain. So this tells about the types of inputs, that is unit input, unit ramp input, unit parabolic, unit impulse, and the symbols for this one is unit step input u of t, ramp input r of t, and impulse input delta of t. The response here for unit step input is in a S domain, that is 1 divided by s, 1 divided by s square, 1 divided by s cube, and here it is 1. So this one we have got it from applying the Laplace transform for this type of expressions. Okay, hope you have understood. For any details, contact at my email address, that is naveen.kalal at canaraengineering.in. Thank you.